We need general techniques for determining when a series converges. We've already seen an example of what's usually called the comparison test. The original series that we looked at was this series. That's the sum n goes from 0 to infinity of sine squared n divided by 2 to the n. And that series converges. But remember why. Let's recall how we prove that this series converges. And what we did was to compare it to a geometric series. So 0 is less than or equal to sine squared n over 2 to the n is less than or equal to 1 over 2 to the n. And these inequalities just follow from the fact that sine squared is trapped between 0 and 1. But now what do I know about the sum of 1 over 2 to the n? The sum 1 over 2 to the n goes from 0 to infinity, converges. Right, this is a geometric series. I can even evaluate it. Now what does that tell me about the original series that I'm studying? What about the sine squared n over 2 to the n? Well, the sequence of partial sums for this series are all bounded above by the value of this series. And the sequence of partial sums is non-decreasing because these terms are all non-negative. So I've got a monotone sequence which is bounded above. That means the sequence of partial sums converges. And that's just what it means to say that this series converges. That was a bit quick. So let's generalize this argument, try to formulate it as a broadly useful technique. So here's the usual setup. I'm imagining that I've got two series. I'll use k as the index. K goes from 0 to infinity of a sub k, and another series, k goes from 0 to infinity of b sub k. And I'm supposing that 0 is less than or equal to a sub k is less than or equal to b sub k for all k. I'm imagining that the sum of the b sub k's converges. Right, so I'm going to be assuming that this series converges, and then I'm wondering about this series. Does that series converge or diverge? Well, to study that question, I'm supposed to look at the sequence of partial sums. So that's S sub n is the sum of the terms k goes from 0 to n of a sub k. And now the whole question is whether this sequence converges, because the convergence of this sequence is exactly what it means to say that this series converges. What kind of sequence is that? Well, here's what I know. I know that a sub k is less than or equal to b sub k. And that means if I add up a whole bunch of a sub k's, say the a sub k's between k equals 0 and n, that's less than or equal to adding up the b sub k's, k goes from 0 to n. Now this thing here is just the nth partial sum. Now what do I know about this sum? Well, the rest of the b sub k's are all non-negative, so if I add up even more b sub k's, I'm just making this even bigger. So what I can conclude is this, that S sub n is less than or equal to the value of the series k goes from 0 to infinity of b sub k. In other words, what I can conclude is that S sub n is bounded above. And it's monotone. So let's check that. I want to show that if m is bigger than n, then S sub m is at least as big as S sub n. Well, what's S sub m? S sub m is the sum k goes from 0 to m of a sub k. And I want to show that that's bigger than or equal to the sum k goes from 0 to n of a sub k. But m is bigger than n, so I can rewrite this sum. I can split this sum up. This is the sum k goes from 0 to n of a sub k plus the terms between n plus 1 and m. So k goes from n plus 1 to m of a sub k. And that's at least as big, I hope, as the sum k goes from 0 to n of a sub k. Now why is this true? Well, I've got the sum k goes from 0 to n of a sub k on both sides, but then I've got this extra term over here. What I need to know is that this extra term is at least 0. But that's true because all the a sub k's are non-negative. And if you add up a whole bunch of non-negative numbers, well then the result is non-negative. So this is telling me that the sequence of partial sums is non-decreasing. So the sequence of partial sums is non-decreasing and bounded above. So for the monotone convergence theorem, it converges. Let's summarize that. So here's what we've proved. If we've got two sequences which are related in this way, that a sub k is between 0 and b sub k, and the sum, k goes from 0 to infinity, of b sub k converges, then the sum k goes from 0 to infinity of a sub k also converges. We can also say something when the sum of the a sub k's diverges. Let's suppose that 0 is less than or equal to a sub k, it's less than or equal to b sub k. And let's suppose that the sum of the a sub k's, k goes from 0 to infinity, diverges. And I don't know, what can I say about the sum of the b sub k's? Well, if this series diverges, that means that the sequence of partial sums, the sum k goes from 0 to n of a sub k, that can't converge, right? Because to say this thing converges, to say this series converges. So if this series diverges, this sequence must diverge. But that sequence is monotone for the same reason as before, right? I'm adding up non-negative terms, so as I add up more terms, well, at least it's non-decreasing. So the sequence is a monotone sequence, and yet that sequence doesn't converge. So that means that the sequence of partial sums must be unbounded. Because if it were bounded, and it was monotone, then it would converge, but it doesn't converge. So I've got an unbounded sequence. What about the sequence of partial sums for the series involving the b sub k's, right? So the sequence of partial sums there is the sum k goes from 0 to n of b sub k. This is even bigger than the sequence of partial sums for the a sub k's. This sequence is likewise unbounded. Well, if this sequence is unbounded, then that sequence doesn't converge. And if that sequence doesn't converge, that means that the sum of the b sub k's diverges. And that was fast, so it would help to see the convergence and divergence statements together. Well, here's our standing assumption, that 0 is less than or equal to a sub k is less than or equal to b sub k. And the first thing that we saw is that if the series of the b sub k's converges, then the series of the a sub k's converges. On the other hand, if the series of the a sub k's diverges, then the series of the b sub k's diverges. And it's super important to keep track of the directions of these implications. Right? Here I've got the convergence of b sub k implying the convergence of a sub k, and here I've got the divergence of a sub k implying the divergence of b sub k. And hopefully that makes sense, right? This is saying that as long as you've got non-negative terms, if you're below a convergent series, you converge. And this is saying, as long as you've got non-negative terms, if you're above a divergent series, you also diverge. And let me end by saying that the comparison test is just a ton of fun to use. It's definitely my favorite test.